Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So I'm going to talk about the free momentum experiment. So this is the famous experiment, and it can be done different ways, but let's deal with the most interesting, I think, is the 1, 2, 3 mass circumstance. But we've seen Professor Lewin do the 1 to 2, okay. And the 1 to 3 is more interesting just because of the amounts of energy you produce is more interesting. So I can give this one 100 momentums, the 1 mass, and I will give the 3 mass 150. Okay, so I will make free momentum, and then I'll get a reflection of 50. So the total free momentum, that is the free momentum in the universe, will equal 200. So I put 100 in, hit an object, and now there's 200 worth of momentum in the universe. Now I say that's impossible, can't happen. But they keep insisting these experiments they're doing are credible and these are valid results. Now I showed when Professor Lewin did with his very nice air track that the carts looked like the masses weren't correct because the one mass cart had way too much crap on it to be half the mass of the other cart. So it just wasn't credible. And then when he did it without a spring, okay, accidentally, so when a piece of Velcro didn't work, the experiment didn't produce these results. It produced less momentum forward and a reflection of a minor amount, but you conserve the momentum. Essentially, you didn't make any free momentum. And so we can also do this with penduli, which the Dispar character has done repeatedly. Okay, and my argument is then it gets even more insensible, because frankly, there's no spring, and the elasticity is really very strong in the sense that most springs will lose 10 or 20% of their energy through the interactions, and so steel balls are much better, or glass, in terms of losing less in terms of the interactions. But the idea that you could, yes, you swing it out with 150, and this one hits and swings out with 50. All right, and then those things come into a collision. Okay, so you have 150 and 50 hitting each other, and only 100 pops out. And you have to say, how can that be possible? And then it repeats over and over again. You have 200 momentum swinging, metal balls swinging, and then you have only 100 momentums of metal balls swinging. Sorry, I can't make that make any logical sense. Alright, so I was thinking about the spring ones, okay, and so what happens to the spring when you compress a spring? And so say if I do have 50 momentums come in from this side, and I have 150 over here, but this is in a heavier object, so it's compressing the spring slower with more, total force, but over a longer period of time. And so you can sort of understand, okay, the 50 is coming in faster, so it will hit the spring and start compressing it. And then the 150 is putting its in, and it starts compressing it. And you got to say that, well, the 150 is going to win because it's heavier. Right? The heavy object is going to be the durable one in this case, okay? And so it's going to start pushing the spring in that direction, and therefore you could sort of understand why 200 would come out here, okay, not 100. So 150 comes in, 50 comes in, and you'd expect 200 to fly out the other side. Or in the case that's more pertinent, all right, I would argue that these numbers, okay, what's really happening with the pendulum has to be, okay, in my opinion, that you send 100 in, okay, and in the 1 mass, and the 3 mass, okay, will now leave, okay, with 75, and the 1 mass goes back with 25. Now you have a sensible collision of a 25 and a 75, okay, and you can expect, because the 75 is heavier, it will win, okay, and basically all the energy will come back as 100. So I'm saying that's perfectly reasonable to me, and that's what's really happening in the real world. Now, why do their experiments, such as they are, come out the way they do? All right. So I would argue that I pointed out that the air track has the flaw of that it's producing air. Okay. So when you do an air track experiment on a less than fancy air track, the problem is it's shooting air up, and anything that the carts do, okay, that causes them to in any way tilt on that track, all right, would cause them to exhaust air more out one side than the other side. And you can understand that's essentially just a little jet engine. It's going to give them extra momentum. So if they banged into each other and lifted up a little bit, you could imagine the carts tilting up, they would both end up pushing air out, and they'd both end up having more velocity than they should have if they were relying only on their impact energy. So that's a flaw with the air track. Now I pointed out that the carts they use, they call them low friction carts, but the the flaw is they have like 10 wheels, maybe, I don't know, I never counted, but it's a lot of wheels. All right. Each one of those has a little metal axle, no doubt, and the wheels are made out of metal, and then they put a plastic car on top of that. Okay, so the argument would be is that when you give it some sort of momentum, that there's a bunch of angular momentum caught in the wheels. So the wheels momentum, you can't see that as linear momentum. All right, so all the matter going up and down and left and right inside of the wheel, all of that energy, okay, is completely separate in a way from the linear motion of the cart. So if you want to know its total momentum, you have to add the momentum not only of the mass of the cart, but the mass caught up in rotation. It's doing more than one thing is the argument, right? You can understand that the atoms in that cart aren't just going that way. That the atoms are, the wheel atoms and the axle atoms are moving a lot more other directions. And you have to add all of that to find the total momentum of the cart. So that's the real flaw in their low friction carts, is that they're high angular momentum carts. So they could be, it could be 25% of their total momentum could be in the rotation of the wheels, depending on how fast you move the cart. So the faster the cart goes, the more energy will be in angular rotation, and the slower the cart goes, you can understand the slower those little wheels are turning, the less energy is in the turning of the wheels, and the higher percentage of the energy will be in the linear motion. So it's clearly a huge potential bias, you could argue. All right, so again, we'll go back. So that's some context. And so they don't do the cart experiments as elastic experiments. So I haven't seen anybody do an air track or the carts by allowing metal to hit metal, just elastic. They always put a spring in there, and that makes it super elastic, is a term for that. So it's not elastic, but it should work when you do it just elastically, and yet nobody does it. So clearly the springs are just a complication. So it's worth talking about what a spring is likely to do in a collision between objects that have uneven momentums, or i.e. energies. So we'll do that in a moment. Right, so I haven't really thought about all of this ahead of time, so I'm just doing this partially for my own to give me something to think about. Okay, so you're going to compress a spring. All right, and so the question is exactly what does the spring do as it's being compressed? So we know if I just put pressure in on one side, it's all kind of simple. The spring just absorbs it in one direction, all right, and it compresses, and then it stops, and then it uncompresses, okay, when it's done, when the force has finished using up its energy. Now, if it was gravity, it would just stay compressed, right? Or it would oscillate. It would go deep and then come back and finally stop at the weight of the object if it was in gravity. But we're just using a linear motion here, and there's no force that's constant, doesn't have an engine or anything else. This is something where the energy will essentially be absorbed by the spring, and then the spring will release it. Now, the truth is we don't know how good these springs are, so in the disbar case, it's a crappy little spring on a matchbook car. And so I wouldn't expect it to be able to return more than, 80% of the original velocity or momentum, that it would lose, a substantial amount. But we don't have any evidence of that because he didn't do that experiment. But he should first, just to show how good his spring is. Anyway, and now we also know that speed matters to these springs in the sense that, you can compress them. You can hit them with a force that's going to make the spring move faster than the spring's capable of doing. And that will also change what kind of reflection you get. But you can't make more energy. You can't hit a spring in some way and actually make more energy. You can change how fast the force leaves. So there's something we can know about a spring, is that if I compress it to that, I put energy in, I compress it, all right, that it does have a maximum speed that it can release at. So there is a speed that the spring can move if there's no weight on it. So if there's no mass, the spring will move at a certain velocity, and we know that's the maximum velocity it could ever give something. It can't give something a velocity that's faster than the spring itself can move. All right. So that's just a logical statement. And that the spring, if there is no mass, will reach its maximum velocity, fly past that because now it has to stretch, and then it will oscillate back and forth with the energy and losing, maybe 20% with each oscillation. 10 anyway, let's say. Okay. All right, so now the case of these examples is that there's both sides are being compressed. So you're compressing the spring from this side, and you're also compressing the spring from this side. Now the simple argument would be is that if I have the same mass or the same energy compressing both sides, that it will just duplicate, okay, what it would be like if, say, if I plowed a 100-mile-an-hour car into a spring, I could expect a certain amount of compression. And if I did 250s, all right, I could expect it to produce the same compression in the spring because I'm pushing it from both sides. So I'm going to create the same final compression. And so clearly 250s are going to equal 1/100, in the sense that it's going to be the same. As far as the spring is concerned, it's the same force. It's because it's being, instead of being just pushed from one side, it's being pushed from both sides, so it's compressing it essentially twice the speed. You'd understand it would take, it's twice the speed of compression because it's doing this the same time as it's doing that, and so it's going to meet in the middle quicker than it would if it had to go the full distance. So obviously it's twice the speed of compression. And that gets to a sort of a Mythbusters video where they did a similar experiment to this, and the real point, the real takeaway isn't so much that both cars absorb the same energy as if they hit a brick wall. I mean, there's no difference in if you smash the cars, you'll get the same result. Now if you smash a car in between the cars, okay, like the cars are indestructible and the car in between isn't, yeah, it crushes twice as much as if one car had hit it, obviously. And, but the real point is that the thing they didn't consider would be that the G-forces on the people in the cars are going to be completely different. So if you hit a brick wall at 50 miles an hour, okay, you're going to slow down, say, in 1 second, okay. And if you hit another guy going 50 miles an hour, you're going to do that same thing but much quicker. So now it's only going to be a half second. So you've increased how much you're going to have to decelerate, how quickly you have to decelerate. So although the car is broken just as much as hitting a brick wall, a person in the car, okay, will be hurt more because they're going to have to decelerate quicker. All right. So what else? Yeah, so I was at this, how the spring absorbs the energy. So if there's energy coming from both sides, the real point would be is that the spring doesn't care. All it's going to do is absorb pressure, and collapse until the pressure stops. So the spring is basically going to behave as if there was only energy from one side. It's going to compress until there's, the total pressure is reached, and then it's going to expand. So it will come to a point where it stops moving. Say, the pieces of the spring will stop moving, and it won't produce any energy out until it first goes to that stop position. So first it has to absorb the energy, then it can start expanding. And the argument is that if one side has more force, then that side, okay, this side will be absorbed, the energy on this side will be absorbed, and the other side now has to create the pressure because this one's already done putting its pressure in. So say the faster object put its pressure into the spring, it's already in the spring. This side has to essentially move the spring to continue making pressure with this other side. And so for there to be added pressure, the whole spring and the object have to both be moved in that direction. And once the direction is established, then the spring opens in that direction. This will be the side that has less pressure, okay, and the side with the slower, heavier force, the higher torque, that's the side that's going to be still compressing. So the spring is going to say, well, I'm going to go to where there's, just like heat, it's going to go where it's colder. The pressure is going to go where it's less pressure, and it's going to be less pressure this way because everything's moving that way than going the opposite way, which is against the thing still pushing. Alright, so in a sense, yeah, this side can still push while this side is starting to expand. It might be possible, but I'm not sure of that. But the point would be is that you're started giving it, so you come in with this heavier object with more momentum, it starts to move the whole spring and the object, and then the spring starts to expand and it pushes in both directions, but obviously it can't push in the that direction as easily as it can push in this direction until this thing stops. So when this thing stops moving, then the spring can push this way, but it's already lost some of its energy going this way, and so when it does the 50-50 thing, it's 50-50 of whatever's left, 80% or 70%. Whatever's left in the spring goes 50-50 in the both directions. So this ends up getting a total that's lower because this object pushed this and the spring already started using energy in this direction. You already started this one moving, and so it's already got a portion of the momentum, the total, from the spring. So the spring only has whatever, some lesser percentage left, and then it gives that lesser percentage to both sides. I think that's a reasonable explanation. So when this stops, then the spring can expand both ways, but it can't expand both ways until the heavier object stops moving. And it stops moving after the lighter object, would be my argument. Alright, so back to relevant to this experiment. So again, it's this whole idea of creating an oscillator where it's possible. And I don't know how, if I put a, let's just imagine we had a pendulum, but we had springs, so it had the idea of 100% elasticity, but there was a spring in here, and how that would make any sense in terms of this experiment, where you could put 100 in, get 150 here, alright, and still have 50 bounce back this way. How can I compress the spring with 100 and then push something with 150? I mean, it just doesn't make any sense. How can the spring store that and then put 50 out this way? Still have enough to do that. I mean, where did it get the extra momentum from to make that happen? And then when these things come back into each other, we know that if we don't have a spring and we have crushable fenders, we know that the crushable fenders are going to crush, probably 100 here and 100 here. We know that when the unequal things hit each other, that the 50 thing is going to be hurt more than a brick wall, because this isn't equal momentum, it's 3 times more momentum. So the 3 times more momentum is clearly going to keep crushing this beyond what it would crush if it just hit the brick wall. So it's going to take the bulk of the crushing. It's going to take more than if it hit a brick wall. And this is going to take less than if it hit a brick wall, because it's giving the other things crushing for it, slowing it down. It's decelerating by crushing. But we know we're going to get the full 200 worth of crushed fenders. So you're somehow saying that merely by putting a spring in here, I can avoid the 200, the same energy in terms of crushed fenders will somehow be mitigated, and I'll only have 100 bits of momentum come out of the collision. So 200 goes into the collision, only 100 pops out. I'm saying, how can I make sense out of that? And it keeps doing this. It's an oscillator. It has to have, there always has to be the same energy in the system, ideally. And so how can it have 100 pieces of matter moving and then have 200 pieces of matter moving and keep oscillating between the two when the same energy is producing it? So that's why it will never, I'm not going to accept something less than a perfect experiment. Okay, so it's going to have to be a perfect experiment demonstrating this as a possibility. It's going to have to be really clean and really clinical and really good. It can't be crap piled on matchbook cars, because this is a lot to overcome. The idea of creating free momentum isn't, a ballistic pendulum can't even do it. I mean, you put 2,000 joules into the ballistic pendulum, it can only pull out 1.7. I'm just saying, why can't the ballistic pendulum, if free momentum is so easy, why can't it make free momentum? Come on. You got to understand why you have a little higher burden of proof than, rickety matchbook cars, where, I mean, frankly, timing gates are really great, but, the flags have to be a certain, the bigger the flag, the more accurate it's going to be. The smaller the flag, the less accurate it's going to be. This whole timing thing. So, depending on, it means, all that stuff means a lot. And obviously, there's all kinds of other questions you could ask. I mean, in the particular video he did, he has a flag on one car made out of paper, and then the flag on the other car is made out of cardboard. Why would you make the flags out of different material? Even that doesn't make any sense. But anyway, those are small defects, and the argument still would remain, it's pretty implausible that I can throw something at a wall the wall yields, that is, it absorbs the energy. It absorbs twice as much energy as I put in. Okay, so I throw the ball at the wall moves with twice as much energy as I threw at it, and the ball comes back to me with the same amount of energy I threw it at. So I get a perfect reflection back with the same energy I threw the ball with. It pushes my hand back with the same amount of force that I let the ball go with. And the wall's moving twice as fast? I don't know how people can believe that's true. That can't happen. If the wall moves, the ball ain't coming back. It ain't coming back with the same energy I threw it with. That's for sure. So anyway, so that's the context. So, the expectation that I'm going to be convinced by these little rickety experiments, I think, is fairly unrealistic.